Next, we have our first speaker, Professor Steve Elliott from the Institute of Sound and Vibration Research in University of Southampton in the United Kingdom, where he served as a director from 2005 to 2010. Professor Elliott's research interests are mainly concerned with the connections between the physical world and digital signal processing in relation to the active control of sound and vibration. His work has seen successful demonstration of active control in cars, helicopters, and propeller aircrafts. Today, he'll be sharing on noise source identification and control of pedestrian warning sounds in electrical vehicles. Professor Elliott, please.
So my name is Stephen Elliott. I work at the Institute of Sound and Vibration Research at the University of Southampton. And I'd like to thank Professor Gann for inviting me to this very interesting webinar. And I'm just sad that we can't all be there in person, that we're doing this remotely. So what I would like to talk about is noise source identification and the control of pedestrian warning sounds, particularly in electric vehicles, as a contribution to urban noise. So specifically, the things that I like to talk about are the kinds of noise sources that you get in road vehicles, then specialize in tyre noise, because that becomes particularly important for electric vehicles. And then finally, talk about pedestrian warning sounds, which again are particularly important for electric vehicles and urban noise. So the noise from vehicles is typically measured on what's called the pass-by noise test, and these are standardized. And in the past, these have been measured by driving the vehicle past a stationary microphone. So the vehicle has been driven past a stationary microphone, and the noise level at that microphone has been measured under standardized conditions. And if you do this for electric and conventional internal combustion IC cars, then and you plot the noise level that you measure against the speed of the vehicle, then what you find is that for conventional internal combustion cars, the noise comes down and as the speed reduces, but then once you go below a certain level, the noise is louder than you measure from an electric vehicle. So below about 20 miles an hour, then a conventional vehicle can be significantly louder than an electric vehicle. And if you look at the sources of noise within the vehicle, then basically you can divide those into two sorts. There is propulsion noise, which is typically coming from the engine, and then there is what's called rolling noise, which is the interaction between the tyre and the road. And I think what is happening is that in an electric vehicle, there is no propulsion noise, and this is particularly important at low speeds for internal combustion engines. And so what is happening is that at low speeds, then the noise from the electric vehicle is being dominated by the tyre noise. And so tyre noise is particularly important for electric vehicles. And in recent years, then pass-by noise, the measurement has been developed so that instead of having to do these tests outside, which are subject to very environmental changes and variables, then there have been methods developed to do these inside. So typically what happens is the vehicle is placed in an acoustic room with absorbing walls. It is put on what's called a rolling road. So the vehicle is stationary, but the vehicle is driving a road, which is a big cylinder underneath the floor. And then an array of microphones is placed in the room as well. And traditionally, the way that these microphones have been processed is that in order to synthesize the sound at a single microphone as the noise goes past, then what happens is that this microphone over here in the internal arrangement is used first, because that's going to be the one when the vehicle is furthest away. And then in order to synthesize the noise that the vehicle driving past, then a mixture of this microphone, then this microphone, then this microphone is processed together in order to produce the pressure waveform as if this vehicle was driving past a static microphone. So those methods are now in the standards, what this allows you to do is to develop this method, and instead of just measuring the entire noise from the vehicle, then what you can start to do is to look at the individual sources of noise in the vehicle and identify those individual sources, and then synthesize the sound of the pass-by noise from those sources. So for example, you can test a car with one kind of tires, and then afterwards you can just test the tires themselves and superimpose the sound of that vehicle with a different kind of tire on it. So what you can do is you can do experiments in the computer in order to estimate the pass-by noise, the drive-by noise of an electric vehicle with many different types of tire in order to find the quietest one. So the main part of my talk it starts here in terms of the novel work, the new work that we have been doing. And this is a PhD student called Thanasis, who has just finished his PhD, and this work is written up in the Journal of Sound and Vibration this year, and he's writing another paper at the moment to do with electric vehicles. And essentially, the way that he has been estimating the tire noise contribution to the drive-by noise is using a two-step method. So to begin with, what he does is he has an array of microphones around the tire. So this is the vehicle inside the acoustic chamber, and it's driven on this rolling road. So this is the top of a big cylinder where the tire is being driven by. And these microphones here are being used to estimate the sources that exist on the surface of the tire. So this is saying that the sources are the inverse of the responses between the sources and these near-field microphones times the vector of pressure at these near-field microphones. And then once we have got the vector of source strengths for the tire, then what you can do is put those source strengths in a model which predicts the response from these sources to the far-field microphones, and then you can predict the vector of far-field microphones from this vector of sources using this matrix of acoustic responses from these sources on the tire to the far-field microphones. So that's the principle of the method. And looking specifically at the source identification, this trying to identify the sources around the tire, then we have 15 near-field microphones that were used in these experiments. So in principle, we could identify the source strengths of 15 sources going around this tire. But then the synthesis would then be very complicated. And so the question that we've been asking is, well, how many sources do you really need for accurate synthesis? 15 is probably too many. If you only use one, it's probably too few. So how do you decide how many sources you need to use and where those sources are? And we've been using sparse signal processing to do this, using what's called L1 regularization. And the standard method in the literature at the moment is that what you do is you minimize the difference between the near-field pressure and your estimate of the near-field pressure with this vector of source strengths. And then you make that subject to what's called an L1 regularization, which is that the one norm of the vector of source strengths has got to be less than a certain amount. But the problem with this method is that you then identify source strengths at each individual frequency. So potentially the position of those source strengths can vary with frequency. So the new thing that we have done, the novel contribution of this work, is to reformulate this problem, so that what we do is that we minimize the difference between the near field pressures and our estimates of the near field pressures over a whole range of frequencies, and then we subject that to this one norm constraint, again, over this whole range of frequencies. And so what this allows us to do is to choose a fixed number of microphones, and the positions of those microphones will not change with frequency. And the results of one of these experiments that we did was that we varied this regularization parameter. We looked at the error between the measured near field pressure and our estimate of this near field pressure as we increase the number of sources, and the error goes down as you increase this regularization parameter, and the number of sources starts to go up. So if you look at the point where the error reaches a minimum down here, and then you count the number of sources that you need in order to reach that minimum, it's fairly clear that instead of needing 15 sources, you only really need 4 sources in order to get a good reconstruction of the pressure. So this is a graph of the spectrum of the far field pressure at a single microphone that has been, first of all, directly measured when this car was in the chamber. So this is the blue curve is the sound pressure level as a function of frequency, which was directly measured at one microphone, and you can see that there's this variation. And the orange curve here is the result of doing this L1 regularized synthesis over frequency. And so you can see in this frequency region here, then you're getting quite good results. But there is a few problems at lower frequencies. And so what we have to do is to also introduce some standard L2 regularization in order to get a good fit. So the green curve is the final synthesized far field spectrum using these identified 4 equivalent sources. And you can see that that far field spectrum matches the directly measured spectrum really rather well over most of the frequency range. And so what we can say is that this method of measuring the volume velocity and synthesizing the far field pressure is working well using only 4 sources. And to reinforce that, then this is the overall level now, this is the dBA level, measured at all of those microphones in the far field. So we had 14 microphones 7 meters away from the car, which is what the standard says. And again, the blue curve is the directly measured one in the experiments. And if we only use one source, one equivalent source, then you can see that we really do not get a good estimate of the far field pressure. And if we increase it from 1 to 2 sources, which is the green curve, again, we're not really getting a very good representation of the far field pressure. But as soon as we increase that to 4 sources, you can see that at each position, we are predicting the dBA level that is coming from this tire really rather well. And the level is the largest at microphone 5, because microphone 5 is the closest to the tire. And if we were to increase that, and if we were to decide that we were going to use 8 sources, which is the red curve here, then we really do not get very much improvement in terms of the prediction of the far field pressure. So this is really proving the idea that the best number of sources to use is 4, because this gives us a really good trade-off between not being too complicated and yet having a high accuracy. So we're getting deviations of only about ½ decibel between the measured and the predicted pressures. So this is a very good prediction of the noise that is coming from this tire. And in a separate series of measurements in a different chamber, we repeated these experiments in an electric vehicle, which instead of going at a steady speed, which the previous one was doing, then this electric vehicle was being accelerated on a rolling road. And again, we had an array of near-field microphones in order to identify the source strengths, and then an array of far-field microphones to estimate the urban noise that this vehicle or this tyre would make on this electric vehicle. And so you can see that over a period of time that we measured it, the noise level goes up, and this is the spectrogram. And so you can see that the characteristic frequencies which are made by this tyre are increasing as this vehicle accelerates from a low speed to a high speed. And what we have done is we have used again this L1 regularization over all frequencies to identify the number of sources. And what we again found was that with 4 sources, we got a very good representation, a very good synthesis. And the positions of those sources were that there are 2 on the top of the tyres, which are less dominant, but the really dominant ones are on the leading and the trailing edge of the contact patch. This is the tyre on the road. So again, the light blue curve is the measured one, and the green one was the one that is synthesized from the one tyre. But in this case, then what we also did was we measured the sound power that was coming from the other tyre as well. And you can see that when we add the 2 tyres together in order to get the orange curve, we really get a very good match, even though the opposite tyre, the tyre on the other side of the vehicle, is only contributing a rather small amount. Then it turns out that that's really quite important in order to get a good synthesis of the noise from the vehicle in that case. So this method seems to be a very effective way of estimating tyre noise, and so potentially tyre manufacturers could publish this data on the source strengths of their tyres at different speeds, and then vehicle manufacturers could automatically go through different tyres in this kind of synthesis procedure in order to estimate the noise and listen to the sound of different vehicles with different tyres. For the final part of my talk then, what I would like to do is to talk about the need for pedestrian warning sounds, particularly on electric vehicles. So there is a feeling that electric cars are too quiet in the sense that the vehicle sounds are used by pedestrians and cyclists in order to safely navigate different traffic situations and to know where vehicles are. So there is a concern that electric vehicles do not provide this feedback, and that the natural noise from the vehicle is too quiet. And so normally then on an internal combustion engine, then the sound from the vehicle would provide information about where the vehicle is, how quickly it's going, how quickly it's accelerating, and what maneuver it's doing. So all of these things are potentially missing from electric vehicles. So on the one hand, then there is a feeling that electric cars are too quiet. But then on the other hand, then all vehicle sound contribute to urban noise. And so if you were to make the vehicle louder, then it would increase noise pollution. So there is a tension, there is a trade-off between, on the one hand, providing enough information about the vehicle for it to be safe for pedestrians and cyclists, and on the other hand, not making it so noisy that it contributes to environmental and urban noise. And coming back to this graph of the noise level against the speed, and just reinforcing the point again that at low speeds, electric vehicles are much quieter than internal combustion vehicles, then these measurements have measured that there is maybe a 20 decibel difference, which is very significant between the sound of an electric vehicle and the sound of an internal combustion vehicle at low speeds. And as it says, surveys have suggested that electric vehicles are more frequently involved in collisions because people can't hear them. And certainly in Europe and America and in Japan, there is legislation that electric vehicles have got to be fitted with artificial mechanisms in order to generate warning sounds in order to prevent these collisions and make them safer. But the counter argument is that some surveys have argued that there is a danger of increasing the overall noise levels. And so again, these studies have suggested that there is a trade-off between warning people and not increasing urban noise. So if we look at the requirements for a warning sound system, then there are various characteristics. If you look at the type of sound that you've got to make, then it's got to have good detectability and recognizability, and it should blend into the soundscape of the urban background, so that it shouldn't, although you need to be able to recognize it, it shouldn't be annoying for everybody around. And all of those characteristics are not so much physical characteristics as psychoacoustic characteristics. So these are to do with the way that the sound is perceived rather than the way that the sound is made. And also different manufacturers, car manufacturers, will want to have different kinds of sounds potentially because they have a certain brand image for their vehicles, and so they want to do marketing. So in the same way that different cars sound differently, then different manufacturers will want different sorts of sounds. And there is a standard that says that the frequency range of these things should be between about 300 Hertz and 5,000 Hertz, and that the spectrum and the noise level needs to change with speed, because the change of the sound with speed is what gives you this perception, this knowledge about what the vehicle is doing. And also it's useful if the sound is directional, because then what you can do is you can make the sound come out of the vehicle, and the standard says that it's got to be plus or minus 60 degrees at low frequencies and plus or minus 30 degrees at higher speeds. And you can focus the sound in the front of the vehicle in order to warn the pedestrians without increasing the noise on the sides of the vehicle. So the pedestrians would be here, and you want high sound pressure levels, and you want low sound pressure levels at the side, because you don't want to increase the urban noise. And there is another PhD student at Southampton called Nick Kournanis. He's been working with Jordan Chia on a very interesting part of this project, which is to make these sounds adaptive depending on the environmental sound that you have. So their idea is that you have a microphone in the car, and that microphone is measuring the background noise level, the background spectrum of the urban environment, and that noise level is then mixed with some warning sounds, and then you have a psychoacoustic module which is modeling the response of the ear and the masking in order to decide how high or what spectrum of warning sounds you need to have in order for those warning sounds to be perceptually relevant above the environmental noise, but not make more noise than they really need to. So this is an example of the spectrum of the noise, and the base warning sound, the standard warning sound, is this blue one here. So this has been decided by a manufacturer that this is the noise that they want to make, and the standard sound that would come out at a given frequency has got this spectrum. But in this case, then the environmental noise is actually higher than this base warning sound was designed for. So this is the environmental sound, and you can see that the base warning sound is quieter than that environmental sound, so it wouldn't be heard. So what this adaptive system does is it then adapts the warning sound so that not only the levels are above the environmental noise, but actually it changes the spectrum so that it's more perceptual above the background noise as well. And going in the other direction, then this is a case where the environmental noise is lower than the designed warning sound was meant for. So again, the base warning sound is the blue one, and now the environmental noise is lower, and so the adaptive warning sign sounds have now been turned down, and again the spectrum have changed, so that this spectrum has changed very much more than the lower spectrum because of this psychoacoustic effects. And so what you get is that you get a sound which is always perceptible above the level of the background noise, but is never so loud that it is annoying and is increasing the urban soundscape. So that is one aspect of the work which Nick has been doing for his PhD at Southampton. And another aspect of the work which he has been doing has been looking at how you could implement these potential acoustic sources. And in the past, various suggestions have been made. There was a large European project called Evader, which used an array of loudspeakers on the front of the car and beamforming on those loudspeakers. And other methods which have been suggested are to use a parametric array on the front of the car to generate a very focused beam of sound. And in the past, we have also looked at using an end-fired array made from a pipe with a whole number of holes in it, so that you have a single loudspeaker at the end, and the sound coming out from these holes generates an end-fire array with a very directional source here. So all of those have been looked at in the past, but Nick was interested in using a different method of doing it. And the method that he was looking at was to use structural actuators. So these are small shakers which are mounted on the body of the car, and they're mounted on the outside of the body for these tests. But obviously in a practical implementation, they would be mounted on the inside of the body so that you couldn't see them. In this case, the sound is radiated because of the vibration of the panel. So instead of having loudspeakers, the idea here is that these shakers shake the panel, and that you shake the panel in such a way as to generate this directional sound. So multiple actuators are used to control the vibration and the directivity of the resulting sound. And the idea is that this would be less expensive and certainly more durable. You can imagine that having loudspeakers on the front of the car, they would be subject to damage from stones and things like this. And again, we did some tests. We had a collaboration with IDIADA in Spain, a part of this PhD. And so on this vehicle, then Nick had an array of shakers at various positions on this car, and then he measured the sound at these microphones, and then he looked at driving these actuators in different ways in order to get different directivities. And in particular, then he looked at using an array of actuators on the front bumper, but also then the car manufacturers were interested in putting the actuators in different positions. So he also tried putting the actuators along the door of the car, or on the bonnet of the car in this direction, or on the bonnet of the car in this direction. And this one in particular, we thought might give us particularly good directivity. But again, in these tests, the actuators were put on the outside of the car in order to just make the experiments easy. But in a production system, then the actuators would obviously be on the inside of the doors rather than the outside in order to hide them away. And these are some results, and they are presented in terms of what's called the acoustic contrast, which is the difference in level in one zone, which is where you want to generate the sound, which is called the bright zone, compared to another zone where you don't want to generate the sound, which is called the dark zone. And the ratio of the average levels in those two zones is called the acoustic contrast. And these are graphs of the acoustic contrast as a function of frequency. And you can see that for this particular arrangement here, which was been put on the bonnet on the broadside, then what we're measuring is something like 10 decibels of acoustic contrast over a wide frequency range. So the sound in the region that we want is about 10 decibels louder than the sound in the region that we don't want. So this is warning the pedestrians. This is just increasing environmental noise. So we want this number to be as large as possible. So on the bonnet, we get about 10 decibels. If we put them in a line on the bonnet, which we thought was going to be a very good arrangement, then it turns out that that's really no better than putting them across the width of the bonnet. So you don't really get very much improvement in the contrast using that arrangement. And on the door, then it turns out that in the forward direction, then you get a particularly poor contrast. So putting them on the door seems like a really bad idea. But interestingly, putting them on the front bumper, which is where the obvious place to put them would be, and it would be most convenient to put them there, then at these important psychoacoustic frequencies around 1000 hertz, then you start to get acoustic contrasts which are maybe 20 decibels rather than 10 decibels. So this seems to be a particularly good place to put these loudspeakers on the front of the bumpers here. So in summary of this talk then, what I've concentrated on is the noise from electric vehicles compared to internal combustion engines, ICE vehicles. And what we've seen is that the noise from electric vehicles is much lower than that from internal combustion vehicles at low speeds. And this has generated two research projects. One of them is that it means that for electric vehicles, the noise from the tires is much more important at low speeds than it would be in normal vehicles. And so characterizing that noise at low speeds becomes very important. And we've developed a way of doing that by calculating the source strengths at a relatively small number of sources, and then using those source strengths in order to synthesize the far field pressure in drive-by tests. So that was the first project that I described that Thanasis was involved in. And then the second project that I described that Nick was involved in was looking at using additional sounds that we could generate on an electric vehicle to warn pedestrians. And what we were particularly trying to do was to make sure that there was enough sound to warn the pedestrians, but not so much sound that it actually increased the environmental sound. So we were trying to get this balance between warning and not increasing the urban noise. And that there was a psychoacoustic method to do that. And then finally, I was looking at how that might be achieved by using an array of vibration actuators on the car structure and driving them in sort of a beam forming method in order to get the right directivities. And on a final note, that I would note that both of these projects were supported by the European Union in what's called an integrated training network, and this training network was called Pass-by Noise version 2. So this was a very successful example of two very good PhD students who came from other parts of the European Union and worked at Southampton as part of a large team working on pass-by noise for electric vehicles. And these were the two particular projects that they were involved in. So I hope that that's given you some idea of the work that we've been doing in this area, and I'm very happy to answer any questions that you may have about that. So thank you very much.
Thank you, Professor Elliott. We have some feedback that the resolution of the slides are quite poor. I'd like to apologize for that. But rest assured, the slides will be made available to the attendees after the session, so you can just refer at your time. So now, If you have any questions, please feel free to submit your question using the Q&A button on your devices, and remember to upvote those questions that are of interest to you by clicking on the thumbs up. Next, we have our second speaker, Professor Woon Sing Gan, Director of the Smart Nation Lab at the School of Electrical and Electronic Engineering, NTU, Singapore. Professor Gan's key research areas are centered around sound perception and audio engineering. One of his current focus is on fusing Internet of Things with deep learning for the classification and localization of urban sound at the edge. This will be further illustrated in his talk today on audio intelligence monitoring at the edge in urban environments. Professor Gan, please.
Hi, everyone. Thanks for joining us in this webinar series on urban noise. My name is Woon Sing, and I'm currently leading the Smart Nation Lab at the School of Electrical and Electronic Engineering at NTU, Singapore. I would like to first of all thank Professor Elliott in setting up the stage of the first webinar sessions on sensing of noise sources. And I would like to continue with the same theme on audio intelligent monitoring at the edge, AMI for short, in our urban environment. My talk today will cover the following key points. First of all, I would like to say why urban sound monitoring is important, why implementing AMI is challenging, and how the data-driven AI model can be used to overcome these challenges, and why we are adopting an edge cloud architectures for our urban sound monitoring. And I will demonstrate the visualization tools that we have created. Finally, I will also say something on our real-time performance results of AMI and their potential applications. So, first of all, why urban sound monitoring? Urban sound contains rich information that can be extracted and digitally derive many useful information of our urban environment. Therefore, a simple sound pressure level meter is no longer enough to tell us the whole story of our living environment. Let me further elaborate and draw an analogy. A sportsman wearing a smartwatch to detect his pulse rate and heartbeat so that he can know his body condition during exercise. Similarly, we can use smart sensors to detect our city pulse, diagnose the types of sound events, and perform prognostic on the sound quality of the environment. So there are several interesting examples using acoustic sensing around the world. For example, in New York City, USA, there's a project called SONIC. It stands for Sound of the New York City, where large-scale urban noise monitoring in New York City is being carried out to better understand noise sources and noise events. They use low-cost monitoring device to detect certain urban noise complaints coming from construction noise and engine noise. In Italy, a project called Dynamap deploys sound pressure monitoring device to detect noise pressure levels around the highway in real time. In another European project, sound signal is being used to determine the traffic flow conditions. For example, when the sensor hears sirens, they will change the traffic lights in the ambulance favor. Sound sensors can determine the volume of traffic at a particular location and also change the traffic light to smooth out the traffic flow. In China, acoustic camera is being used to detect car horn in highway in some of the cities and penalize drivers that create this annoying nuisance. So in a 2017 special issues on applied acoustics, on acoustic in the smart cities, there are several examples on using digital sound technology for urban sensing. For example, in UK, smartphone is being used to collect qualitative as well as quantitative descriptions of the soundscape recorded through their smartphone. and gathers people experience through questionnaires. In Japan, a research group proposed to use machine learning-based scheme for classification of typical urban sound. In Singapore, my group has previously come up with a noisy vehicle surveillance prototypes to identify vehicles or those vehicles that have illegally modified their car engine and exhaust. In France, researchers are using smartphones to perform crowdsourcing of noise data and checking the accuracy of the mobile technology compared to the Class 1 sound meters. So from all this current sound sensing deployment, there are several key advantages that can be carried out using acoustic sensors. There are, first of all, availability of low-cost MEMS microphone, which make it attractive to scale and deploy widely. It further has an omnidirectional sensing, which make it easy to deploy. Further, compared to CCTV camera, they are less obtrusive and not susceptible to occlusion and lighting. It can also complement the vision to give better awareness of the environment, like having both digital eyes and the digital ears at the location. Next, I would like to highlight why digitizations of urban sound is important and how the data collected can be used to set up an objectively driven urban noise regulations. Instead of simply relying on noise complaint that cannot be accurately accounted for and is label intensive, a smart sensors can listen in to the environment 24/7 and plays an important role in detecting key noise events through AI algorithms and provide a richer description analytics of the urban sound, which can now be mapped out into a residential area over time, and mitigation measure can also be carried out more effectively. So ultimately, we want to develop a set of objectively driven urban noise regulations. However, audio intelligent monitoring is challenging. So the number one challenge is the complexity and high variabilities of our sound environment that make it difficult to implement. Let me further elaborate. Unlike speech and music signal, there's no hierarchical structures or temporal dependence in the environmental sound. There are similar acoustic properties among sound types. And furthermore, the multiplicity of the sound in the environment make it difficult task, even for humans, to recognize the individual sound types. Furthermore, sometimes there's no clear distinction between the foreground and the background sound objects. We also need to build a machine to detect and classify multiple sound sources fast enough to run in real time and still low cost for wide deployment. So for AI to work well, we know that data sets are of prime importance for us to train a reliable deep learning model. So without a rich database of the residential areas, performance will be compromised. So we take some inspiration on how human hearing mechanisms in order for us to build a digital ears. We have a very powerful hearing mechanisms. So when you close your eyes, our brains and ear have this super ability to detect multiple sound types and pinpoint the direction of the sound source. And it has the abilities to recognize also the loudness of the sound. Furthermore, human hearing mechanism has this remarkable ability to focus auditory attention on the particular sound stimulus, like focusing on the single conversations in a noisy room. This is what we call a cocktail party effect. So the question is whether we can replace our human ears and brain with a microphone and the AI chips to do the same jobs 24/7 that can be positioned in a remote location? The answer is a growing yes, as we are seeing many great progress in machine listening carried out in different labs and in international competitions. And I'll share a work with you that's being carried out in my labs. So we put together a 24/7 smart ears that can be deployed at the edge to perform inference of the audio events, the noise types, sound pressure level readings, the duration of the sound event, timestamp, the starting and the ending of the sound events, the direction of the arrivals, frequency of the events, and other informations. So all this functionality can be built into a low-cost IoT device unit, which consists of a microphone or microphone arrays, a 4G GSM modem or Wi-Fi units, and a low-cost, low-power embedded processors. Since we are inferring at the edge, there will not be a need to push all the raw data to the server for analysis, which greatly reduce the communication bandwidth and latencies to respond to any events on the ground. There is no raw sound data will be stored in the unit after inference has taken place. We just need to send bite-sized metadata instead. Therefore, there's a great saving in terms of communication bandwidth and power consumption. So this slide shows our outdoor deployment, which is basically built in-house in our labs and installed in a public place. The outdoor unit's hardware specification is shown in these tables. As you can see, this unit is meant for outdoor setting. There are several considerations for protection against the elements and the ease of maintenance. The power consumption is also low at 6 watts. We are also building a solar power version of the outdoor units currently. We also built an indoor version that can be fitted in the ceiling of the room, but I will not be showing the indoor unit in this presentation. In our work, we adopt a holistic development framework. We gather data from multiple sources, from sensors, files, and database. This data would need to undergo a tedious pre-processing, augmentation, and labeling before they are ready to be used for training a deep learning models. A good deep learning model will extract features in the time frequency pattern of the sound information and be able to generalize for unseen sound signals. In our system, we not only need to extract the sound class, but also need to detect the sound direction, which increase the level of complexity. All this processing will also need to come under different real-time constraint or requirement for different use cases and platforms. So let me show you the details of a classification of our sound classification problems, where we use a conventional approach in a training and inference phase of a deep learning acoustic model, so that to recognize the different types of sound events. So we can either detect a prominent sound event, what I call the monophonic events, occurring in a single time frame, or multiple sound events, what we call polyphonic sound events, occurring simultaneously at a particular time. So the job of a deep learning model is to extract key features from the raw data and infer the respective sound events. So there are different types of signal processing techniques at the front end to extract the basic acoustic features through different types of transformation, such as spectrogram, log-mel spectrum, etc. Besides classification, we also need to derive the direction of arrival of sound source through microphone array. In our case, we are using a planar circular array which consists of 7 MEMS microphones, 6 MEMS microphones located at the circumference and one MEMS microphone at the center. So we will have to develop a model that can both perform the sound classification as well as the corresponding direction arrival estimation. There are currently different state-of-the-art approaches in combining these two models. Some are using adjoint models, while others are a combination of deep learning sound classification with a DSP-based direction estimation models. All of these have their strength and weakness. And I will introduce a new approach that we have recently developed that best match the sound event classifications with the sound source localization. We observe that if we separately train the sound classifications and the direction arrival models, we can derive 2 separate timestamps as shown here. The timestamp contains the onset and offset of the sound class that we detect, as well as the direct onset offset of the direction of the sound source that we estimate. By matching the active segment in the output sequence of the sound event detectors and the output sequence of the direction of arrival estimators, we can associate the sound classes with the corresponding direction. So this process has been found to be quite powerful in improving the performance of classification and direction arrival. The figure on the right shows the ground truth, which is the actual sound class event with their corresponding directions. Based on the onset, offset, and the duration of event, we can visually associate the sound classes and the direction arrival of the same events. For example, event 2 may be a sound coming from an engine is being matched to a direction of that engine sound. So we can visually associate the sound classes of these similar events. However, when we are looking at the predicted sequence of the sound event detectors and the direction arrival estimators, they are never perfect. Errors will be made by each of the individual components, can be potentially corrected during this late fusion process, such as a false positive in the classifications. Output sequence can be detected but does not appear in the direction estimations. So the missing segment due to the weak signal in the DOA output, for example, this missing section here, will also be corrected by comparing to the corresponding sound event detected at the classification. So this is a block diagrams that allow us to separately train the classifications and the direction arrivals. The sequence matching network in yellow takes the classification outputs as well as the direction output sequence as input features. So the main components of the sequence matching network is this bidirectional gated recurrent unit, GRU for short, that combine these 2 input sequence and take into account their temporal information. The sequence matching network not only act as a late fusion models to improve the onset and offset prediction for sound event, but also match the sound class and the corresponding direction arrival for each sound events. For each of the time frame, the sequence matching network outputs the number of events, the sound classes, and the azimuth as well as the elevation. Therefore, this approach produces several important information of a sound event. So this modular as well as a hierarchical approach increase the flexibility in designing and optimizing the models for both the classification and the direction estimation. The detail of this work has been presented in an international virtual conference on acoustic speech and signal processing in Spain this year. So we have also submitted these proposed models to participate in this year's international competitions on detection, classification of acoustic scenes and events And the result has just been announced last month. Our sequence model came in second overall, as shown here, in the group ranking. The achieved performance is quite encouraging, with comparable classification error of 20% and F1 score of 82% for classifications, and the localization error of less than 10 degrees, and the highest, we have the highest localization recall rate among all submissions. Next, I would like to briefly talk on the edge cloud architecture that we use in our work and how we can take advantage of the low-cost processors for intelligent distributed sensing and the collation of key city sound house information through cloud. As previously shown, our smart audio sensor nodes can infer sound information at the location, and several of these sensor nodes can be distributed across different locations. So the metadata from each of these nodes can be pushed over the WebSocket to a metadata coordinator in the cloud. Depending on the needs and of the applications, the sensor nodes can be periodically connected to a cloud and upload records into the cloud database, or send an alert to operators when needed. So this rich information can be consolidated and form a powerful database for agency to evaluate different sound analytic indicators, usually for time range and space coverage analytics. Furthermore, the cloud service enables remote access of sensor status. These remote features will allow us to scale up the sensor nodes deployment over time without overloading the manpower requirement. It can also perform over-the-air programming and maintenance, thus saving a lot of manpower on the ground. Our next shows the various visualization tools that we have developed for our urban sound sensing platform. So over here, you see that there's a visualization panel which indicates the sound classes that we can detect on in real time, and also the directional arrival of these sound classes. Besides, it also shows up the sound pressure level, the average sound pressure level, and the instantaneous sound pressure levels. So you can perform real-time monitoring, can be carried out easily, and you can view this in a web application in smartphones. Next, I will show you the sound pressure level reading across time in terms of hours. At a particular location. So you can see that when the data contain the minimum and maximum sound pressure level, as well the average sound pressure level. So if you hover across the data points, you will also notice that there are information regarding the three most dominant sound classes that are happening at that particular time point. We can also enter a specific location and view the sound event happening at that location. So there are different ways to display and analyze this information over time. And we can observe some interesting correlations and trend across the time and space. A Google Light sound level maps coupled with the sound event over different distributed sound sensors is shown in these slides. Note that this animation is a speed up video and does not represent the real situation. However, we can adjust the animation rate over time and observe the correlations of the sound activities in different residential areas and how the space utilization of the areas over different time periods. Finally, I would like to show you a few more real-time performance results and applications to complete my talk. So let me show you short videos on one of our recent work that we have developed to classify the sound event and determine its corresponding direction. Over here, you see an AMI unit that's positioned at the center and is connected to a pan and tilt CCTV cameras. So the AMI will send the direction information to this pan and tilt CCTV cameras for it to pan to the direction of the sound source. So over here, you see 4 speakers. These speakers are placed at the different angles of 90 degrees, 150 degrees, 210 degrees, and 270 degrees. And each of the speaker will be directed with a different sound sources in our system to test out the performance of AMI. The bird sound coming from the 90-degree speakers. So the estimation is shown in the UI here. Alarm sound coming from 150 degrees speakers. The estimated class and the direction is shown here. Next, construction sound coming from the 210 degrees. A bird flowing sound coming from this 270. Notice the camera is panned towards the direction of the sound source. So we showed that this AMI system is able to run in a real-time manner with the classification as well as directional estimation information. This picture shows what we have detected using a sensors that's been deployed in a residential areas. Over here, the green dot at the centers denotes the sensor position, and the north is pointing towards a playground areas. And in these residential areas, we have some key location, the playground, childcare, car parks, etc., and also the walkway. So you can see from these diagrams, our systems detects the sound classes coming from a particular direction. For example, we detect alarm sound or car beeping sound denoted in the pink dot from the car park areas. We detected the vehicle sound also coming from the car park areas, these few dots at the particular directions. And we detect the human voice and shouting activities along the shelter walkway, because this shelter walkway will link to the childcare as well. All right, and also some of this human voice activity at the playground. So in this way, we can have a graphical informations on the sound activities that's happening in the ground, and it provides a useful informations on our urban activities. In all, 80% class accuracy can be achieved with these systems over some 11 sound classes. Finally, I would like to show you some possible deployments of AMI in different use cases, such as aircraft noise monitoring, indoor security, soundscape evaluations, biodiversity monitoring, predictive maintenance in a factory's environment, and also elderly and health monitoring for those who are staying alone. And this system can also be used to detect idling vehicle engines, noisy vehicle surveillance, which I previously mentioned, and also construction site noise monitoring. I would like to thank the funding agencies which funded the Transgrants project. This agency include GovTech, Smart Nation Digital Government Office, and National Research Foundation. I'm also thankful to Amazon Web Service for providing technical support and cloud service credits for us to deliver this end-to-end IoT platform. Finally, I would like to thank the ICA for putting this webinar series as part of the program under the 2020 International Year of Sound. 2020 is the International Year of Sound, which is a global initiative to highlight the importance of sound and related science and technology for all in society. So the International Year of Sound will consist of coordinated activities on regional, national, and international levels. But due to the COVID pandemic, most of the events have been conducted virtually, including this webinar. So you can find out more information on this event by visiting their website. So if you're interested in this topic, you can find out more information in my website. Thank you for your attention.